Morning, everyone. So yesterday we started into our acid and bases section. Pretty much we rehashed what we already knew about acids. I introduced this new name for you here. Arrhenius is the current definition here. They might ask you questions. What is the definition of Arrhenius acid? It's not just Arrhenius acid here has to have an H something. I would use HA, HCl, HBr, whatnot. You have to emphasize here, you actually need to manage to release off this H plus in solution. That's the full definition. In today's lesson, we're going to qualify that a little bit with what's called the Bronsted Lowry definition. Why do I have many different theories? Basically, the Arrhenius theory is a little bit too restrictive, and I basically just slowly and steadily broaden that out. In a very similar fashion here, an Arrhenius base is going to give off the characteristic OH minus. It's not just things that have OH that's our base. They have to be able to actually dissociate and break off this hydroxide before it becomes a base. In this section here, I'm interested in studying a little bit of this H plus in more detail. So this 4.3 here, we didn't quite get to it last day. 4.3, we want to take a look at hydronium. What is hydronium? So let's just start off here looking at hydrogen again. So on the periodic table, we have an H. Hydrogen here is element number 1. It has a molar mass of 1. What's this top number called? Hopefully you were able to say to me here, this is the atomic number. Remember, the atomic number tells you the number of protons. This is what makes hydrogen hydrogen. Hydrogen should have 1 proton. Now, hydrogen is the sort of one stable element here that, the proton already has a mass of 1. Usually this mass number, when I round it to a whole number, well, that's just going to be 1. Usually this number is going to be number of protons plus number of neutrons. In this case here, I already have 1 proton, and I'm actually weighing 1. That actually means I have no neutrons. So if I actually drew out an atom of this one here, a hydrogen atom would actually have 1 proton in its core, right? I know that proton here is a positive charge. Because atoms are electrically neutral, if I have 1 positive, I need to make sure I have 1 negative on the outside. That's what hydrogen looks like. This is so far not the H+. Our characteristic acid particle, H+, has actually lost an electron. So let's think about here, well, what has to happen for an H atom? If I come in with a pair of tweezers, I grab this first electron that I see, and I remove this electron. Well, I haven't touched the nuclei, so basically I'm still going to have the 1 proton. Notice that the one and only shell that I had an electron on suddenly is now gone, because that electron is now loose. We're going to come back to this in the next chapter here called redox. The hydrogen atom has actually been oxidized, and oxidation here is actually a loss of electrons. Here's where we end up with the H+. We're still hydrogen, we still have 1 proton, but if you look at this in this situation, our size has actually decreased by quite a lot. Our atomic radius used to be from the nucleus out to the first shell. Now the first shell was already fairly small to begin with, and now having lost that electron, I don't bother drawing that 1 shell anymore. That electron is now lost free, doing whatever it wants, and now my radius is suddenly just the nucleus. So I just want to emphasize to you here, the atomic radius is a lot tinier. And H plus is actually just a proton, right? We had already said there's no neutrons, right? This one here is a very dense, very small positive charge, right? We just went, the nuclei is typically 1,000 times smaller than where the first shell would be, so suddenly my radius has shrunk by a lot, okay? So that's why throughout this chapter here, you're going to see us synonymously using the word H plus and proton. They're basically the same thing. Having lost the electron, the H, what's remaining, is just a proton. And what ends up happening here is we know charges in general aren't stable. Fortunately for us here, when we release off the H plus, imagine with me I have this 1 proton. That's what I'm labeling currently as H plus. Because this one here is a positive charge, it doesn't like being positive. Charges are unstable in nature. What else is in solution that can help to stabilize it? Fortunately for me, water is a neutral molecule. So overall, water is not charged. We've said it a couple times now, however, because oxygen is more electronegative, even though oxygen was supposed to be sharing electrons with the hydrogens, oxygen actually hogs the electrons towards itself. So that gives the oxygen side a little bit of a negative charge, the hydrogen side of it a little bit of a positive charge. In that case there, what we've formed is what's called a dipole. I always point towards the winner. So even though water overall is neutral, water overall has no charge, water has a side that's negative. If it notices, oh, poor thing, this one here is actually a positive charge, I'm actually going to point my oxygen side towards the hydrogen. And in fact, what ends up happening, oxygen actually has these lone pairs, these extra electrons, and water is actually going to complex. It's actually going to bond together with that H+. So what do I end up with then? So I have an H+, that's my proton. I have the presence of water here. Water is going to attach to it. In total, then, I'm going to end up with 3 H's. Let me see if I can draw a picture here. So I'm going to have the water like this. I'm going to have 3 H's. I would have created a new bond. It is attaching to just the proton that the H+ is. That's going to be written as a H. Water was neutral. This is a H+. So therefore, I've now end up forming a compound that ends up having 3 H's and overall having a positive charge here. This chemical here, H3O+, we're going to give this a name. You can call this a hydrated proton. More commonly, it's written as a hydronium. This is a polyatomic grouping. Most of your polyatomics up to this point have been negative. So far, we've only seen ammonium NH4+ being the positive. This is another example of a positive. So I want to just write this in words for you here. Protons, that's the H+. Protons, H+, do not exist in solution. Right, we said, well, they're charged. They want to somehow get rid of the charge if they can. In this case here, although the water is neutral, water can't actually get rid of charge. I think of this charge here as a hot potato. Imagine so far the proton itself is holding a hot potato. It's really hard because it's the only thing that's holding it. Once it becomes hydronium, at least that hot potato can be spread around the overall charge. Overall, I still have a plus charge. I'm still holding on to the hot potato, but at least I can share it around multiple different atoms here. That allows for a little bit more stability. So protons as H+, they don't exist in solution. Rather, they form this hydronium polyatomic grouping here, and hydronium we're going to write it as H3O+. Right? So not only throughout this chapter here, we're going to be synonymous. Oh, H+, oh yeah, that is a proton. We're also going to say an H+ effectively is a hydronium. These ones here are synonyms. Okay. One way is a little bit simplified, as we're going to see on the tables, but we can always get to the more complex form. Once water is actually complex and actually formed a molecule with the H+, that's actually what it looks like. So let me just give you an example of this one here. Let's take nitric acid, so HNO3. I know this is an acid not because it just has an H, it's that when I drop it in water, it breaks off and it separates off the H+ and NO3-. Sometimes they try to remind you what the solvent, the background is. We're going to always assume that the background is water. You can put that above the arrow there. Right? If we look for this on our tables later on, this one here is a sort of a simplified picture. And basically what it highlights is, well, nitric acid is a combination of an H+ and a nitrate grouping here. All water had to do is water had to separate the positive and negative, and there we go, we get our H+ and we get our nitrate by itself. I was able to release off an H+, I fit that Arrhenius definition to be an acid. Anytime you want to convert the simplified form to the complex form, what's really happening, what does the H+ actually look like in solution? I'm just going to refer to this as the complex form, because this one here is when H+ is complex. It's actually this H+ that's actually going to react with water. Algebra would say if I added water to this side, imagine adding water to this side here. It's the H+ and the water. They're going to complex like I just showed you earlier. They're going to complex to end up forming hydronium. So instead of writing it as just H+, I can actually write it as H3O+ and nitrate. On the other side here is just going to be HNO3 and water. Right? So I want you to just see that both of these equations are actually identical. This is somewhat simplified. It basically just says, this nitric acid just breaks up. It releases off H+. Because an H+ doesn't stay like a proton for very long, it gets complex with water. This second way of phrasing it, a little bit more complicated. It actually says, okay, in the presence of water, the H+ actually has become hydronium, but both of these reactions are actually saying the same thing. And we're going to get some practice later on to actually talk about why we need this complex equation. In fact, this complex equation gives us a nice little connection to our next section here. The nitric acid here is very well H+ and nitrate like this. The simplified form just says, it breaks up. Water has come in and separated the H+ from the NO3-. What we're going to do in the next definition is we're actually going to focus in on this H+. We're going to think of the H+ here as a football. Not only does this HNO3 here release off the football, I want to know where this football goes. Who actually accepts and actually catches the football? In this case here, other than HNO3, the only other chemical I have in the beaker is water. So what's going to end up happening here is we actually have our water. And what the complex form actually identifies for us here is, as the acid, it's going to toss the football over to water. What's going to happen to our equation? Well, the HNO3 is going to be down by an H, down by a charge. That's why we're left with just NO3 minus. The H2O is now going to be up by an H, up by a charge, and that's going to end up forming the H3O plus we had from earlier. And basically what's ended up happening was the football just got passed over. Now it's the water that's actually holding onto the football. And in our next definition, we're going to say, we're going to refer to acid's job is to actually donate a football. The people that are catching the football are referred to as bases. I know normally we don't think of water as a base, we think of water as neutral, but in this next definition we're going to see, because it is a proton acceptor, it receives this football here, it is going to be currently in the base form. Right? So this leads us into our next section here. Again, this first part of acid bases just introduces some of our main terminology, some of the vocabulary that we're going to be using throughout this chapter here. We're going to get to a Bronsted Lowry definition. This Bronsted Lowry definition is a little bit more broad than the Arrhenius definition. Anytime we come up with a new theory in science here, we always want to make sure it's consistent with the older models, consistent with the older theories. Right? So let's have a look here. To be a Bronsted Lowry acid, as I just alluded to here, a Bronsted Lowry acid has to be able to donate protons. Remember, protons are synonymous with H+, we just did this. Donate protons in solution. While a Bronsted Lowry base, instead of it actually forming hydroxide, oh, you have to have an OH minus, you have to be able to release hydroxide. That was the Arrhenius definition. In this case here, we're actually going to say it just accepts protons in solution. Okay? So basically what ends up happening here, we said a proton, it's synonymous with H+. A proton here is a football. An acid is currently holding onto the football, and basically what ends up happening is the acid throws it to the base. The base is currently without the proton, but the base is going to receive this proton here. So for a Bronsted Lowry way of defining an acid-base reaction here, in some sense it is still a neutralization reaction. Essentially an acid-base reaction involves a one proton transfer. So proton is going to be synonymous with the H+. Basically, the football gets passed around. Even though my acid may actually start off with multiple protons here, we always only study one proton at a time. All right? So let's just try out another example here. Let's take hydrogen iodide. This is hydroiodic acid here. In solution, it's supposed to be able to release off H+. So still, we are following the Arrhenius definition. This one here, again, is a simplified form. Basically, water has come in and separated positive for negative. For the acid side, how do we get from the simple form to the complex form? We just saw it's sort of like adding water to both sides. Right? So I add water. Basically, this time it's going to be HI in the presence of water. Ends up forming, well, the H plus and H2O is now our hydronium, H3O plus, and it's now going to have iodide. That's the more complex form. Let's think in terms of footballs now for Bronsted Lowry. H plus is currently holding the football. That means it is currently the acid. It is the Bronsted Lowry acid's job to donate the proton, to give up the proton, to pass the proton over to the base. So overall, this reaction here tosses this football over to H2O. The HI is going to go down by H, go down by charge. That's why it's left with the I minus. The water is going to go up by an H. It's going to catch the football, go up by charge, and end up forming H3O plus. So that's the Bronsted Lowry base. Right? So far, we've been dealing with strong acids. Pretty much in this first section, we will only deal with strong acids, which are all one-way arrows. But technically speaking, you might be wondering, well, if the water is now holding onto the football, couldn't water also throw the football back towards iodide? Totally true. If this reaction here could go in reverse here, then the hydronium here currently has football. That means as an acid, it can also donate a football. It can pass the football back to iodide. The iodide here would now be a base. It's now receiving the football here, and that potentially could go in reverse. So what I want to start showing you here, for these one proton transfers here, we end up having an acid and a base on both sides. I can't have both people be acids. Both people are willing to toss footballs, but no one's willing to catch the footballs. And I can't have both people be bases. They're just sitting around, wait, who's going to give me the football? No one. In this case here, there's always one acid and one base on both sides here. In fact, what ends up happening here is we actually ended up forming what's referred to as conjugate pairs. Now, the important name for us here, Defining conjugate pairs, these are species, these are chemicals that differ by just one proton, by just one H+. That's the only difference between them. So for example, HI, who is its conjugate pair? If I differ by the H+, if I toss the football away, it's in a conjugate pair with I-. HI and I- are a conjugate pair, one on either side of the equation. The water and the hydronium are also a conjugate pair because they also differ by one proton, H3O+ and water. They're on opposite sides. That's important to note here. We're going to clarify this a little bit here. Conjugate pair in general is differing by this one proton. If I currently have the football, I am referred to as the conjugate acid. Right? I'm the acid form. I currently hold the football. I currently have the H+. If I am the conjugate base, it has lost the football, or it doesn't have the football yet. So conjugate base. This one here is without the H+, without the proton. Right? So a couple key notes already is, especially when we have a complex form here, I'm not just saying, yeah, it's the acid's job to release the football. Well, who actually picks up the football? The only thing else in the mixture is water. So water is picking up the football. It's currently acting as a base. I've then ended up trading the football over, and I've ended up forming two conjugate pairs. Potentially, these products here could have come backwards and could come back the way it came. All right. Let's now have another look at the ammonia. Ammonia, like I was saying, ammonia has characteristics of a base. It's very slippery. It's tasting bitter, right? So what does ammonia do? How can I see this one here as a base? It doesn't even have an OH. So Arrhenius sort of has a sort of problem. How is this one here, sort of question mark, how is this one here supposed to produce hydroxide? It's actually the Bronsted Lowry theory that actually helps us out. A Bronsted Lowry, I'm just going to say a Bl base. A Bronsted Lowry base just needs to receive a proton. So let's start off with the simplified form. This is how it's going to appear on the tables later on. Ammonia is supposed to pick up a proton. It's supposed to grab a proton. Well, what does it become then? It's going to go up by an H, go up by a charge, so we're going to have NH4+. Really easy to make predictions because it's just going to be an H+ that's tossed around. Now, I want you to think about it with me here. Imagine I start off with just a solution. We have water in here, and we have NH3s. Although we will see later on there will be the odd H+, there's not going to be a ton of H+ around. So it's unlikely that the ammonia can just luck out and collide, good energy, good geometry, and actually pick up an H+. This one here is a simplified form. The complex form here is going to show you a little bit more detail what ends up happening. How do we get from the simple to the complex form? For the acid case, it was sort of like adding water on both sides, right? The water with the H+ ended up forming hydronium, everything was fine. On the base side, I want you to imagine it's almost like adding hydroxide to both sides. And there's no real chemistry in this here. It just basically, I'll show you what it states later on, but it basically gets us from one form, the form it's shown on the table, to the form that we wanted in. So what ends up happening? So this is going to be NH3, and H+ with the hydroxide ends up forming water. We saw that net reaction before. It becomes an ammonium, and now algebra says if I added a hydroxide to this side, I better add a hydroxide to this side. And there we go. Somehow, ammonia has actually released off the hydroxide that we need to be a base. Let's analyze in a little bit more what's happened. We have already said ammonia is our Bronsted Lowry base. Ammonia is going to be our proton acceptor. Ammonia is going to pick up the football. The question here is, who does he pick up the football from when there's not a lot of H+ in solution? In fact, for water here, water is actually the one that's going to currently have the football. What if water tossed this football over to ammonia? In that situation, the NH3 would go up by an H, go up by a charge. We'd end up forming NH4+. The water would go down by an H, go down by a charge. Oh, that's actually how we end up forming hydroxide. This ammonia here could be a base, not because it dissociates and releases off hydroxide. It doesn't have hydroxide. But in stealing the H+ from water, it's actually water that actually leaves behind the hydroxide, the leftover bit. Let me qualify this a little bit here. So ammonia is a base. Water here is currently the acid, right? Water is the proton donor. It passed the football over. If I'm currently holding the football, I'm now the acid. So NH4+ is now the acidified form, is the conjugate acid form of the base, whereas the hydroxide is the conjugate base form. Again, we've ended up doing a one proton transfer. We have conjugate pairs, two sets of them. Ammonia is in a conjugate pair with ammonium. and the water is in a conjugate pair with hydroxide. Conjugate pairs are on either side of the equation, and on either side we're always going to have one acid and one base, one person willing to toss a football, one person willing to lose the football. Right? Now I just want to emphasize here, as you look at these complex equations, essentially this is another nice hint for you. The complex equation always shows the acid reacting with water or the base reacting with water. It's just like going from how the table actually shows you the equation. For the acid side, it was almost like adding water to form hydronium. For the base side, it's like adding hydroxide. More practice of this a little bit later on. Also, one other interesting note here is, wait a second. Water earlier was actually acting as a base. It was willing to actually pick up the football. Whereas later on, water is actually acting as an acid. There's a special name I give to chemicals that can behave both acid and base. We refer to these ones here as actually amphiprotic. Amphiprotic, sometimes also called amphoteric. An amphiprotic species is a species that can act as either acid or base. Now, up to this point, we just saw our water was neutral. It's not acid or base. In this case here, using the Bronsted Lowry definition, using this fact of it can either donate protons or receive protons, water can actually end up doing both. So an example, we saw water earlier, so it could be a neutral molecule. Right? I can give you examples here. HPO4 minus 2 is amphiprotic. H2PO4 minus is also amphiprotic here. Sometimes just a hint for yourself, which species are likely to be amphiprotic? Typically, we're going to look for, well, it has to be an acid. Typically, it has to have an H. And then to be a base, it has to be able to receive a proton. That proton there has an H+. Usually, it will currently have a negative charge, so that upon taking on a H+, it ends up picking up charge a little bit. So let me just write these reactions out for you here. Let's start off with H3PO4. H3PO4 we're going to see later on is a weak acid. So it's going to release off H+. It's going to become H2PO4 minus. H3PO4 is just acidic. This one here is not amphoteric. Because if this one here were to end up, if hypothetically it ended up picking off a proton, we'd end up getting something like H4PO4 plus. It's unusual for a compound like an acid to pick up a positive charge. Because this doesn't happen, the H3PO4 is not going to be a base. This one here, H3PO4, we can refer to H3PO4 as triprotic. It actually had 3 protons to give. Actually giving off the first proton, H2PO4 minus can further, as a weak acid, can further give off another proton, a second proton. This is going to end up giving HPO4 minus 2. It's always really easy to predict what the products are, is because we're just losing one proton at a time. I go down by an H, I go down by a charge, so HPO4 minus 2. The H2PO4 minus here, as I go left to right, I'm donating a football. So this is H2PO4 minus acting as an acid. But H2PO4 actually was a base of this first reaction. Oh, great. H2PO4 is amphiprotic. HPO4 minus 2, in a similar way here, HPO4 minus 2 here, if it's actually able to actually go in reverse, like given that this is weak, this is a base, fine. But HPO4 minus 2 still has a proton it can release. I can get rid of an H+. I'm now also an acid. So that's why, just as a hint, right? This is not a constant thing here, but basically you can think about, usually for amphiprotic things, usually you will need to have H. So usually it still has to have an H, and it usually has a negative charge. Again, not always. We saw water, right? Water doesn't have a negative charge, right? But the reason why we have a negative charge is if we're negative, we can probably pick up a proton. So if I'm negative 2, I can pick up H+, I can become negative, no problem, right? It's just unlikely for something that's already neutral to then pick up yet one more H+ there, right? So that's how you tell it's amphiprotic. In this case here, when I get to phosphate, this is just going to be basic. I could potentially go in reverse, so this is not going to be amphiprotic. This one here doesn't have any more footballs to give up. I can't end up going forwards. Since while I have it on the board here, H3PO4 here can be referred, this guy here is referred to as being triprotic, because this one here has 3 protons to give. The H2PO4 is referred to as diprotic, 2 protons. HPO4 is monoprotic. Basically, the protic part tells you you have protons, just how many do you have? We usually, anything more than 1, we usually just refer to as polyprotic. So just wanted to introduce to you the Bronsted Lowry definition of acid and base. Instead of worrying about releasing off H pluses, releasing off OH minuses, we refer more so to it's a football that's being passed around. We started seeing these conjugate pairs. We'll end off with this here. Let's do 4.5. That language of conjugate pairs, I had already seen. Conjugate pairs are chemicals that only differ by one proton. And what it actually enables us to do is actually start making predictions for reactions. So let's say I have a reaction here between, let's take that H2PO4 minus. That was one of our amphiprotic guys we had from earlier. It could be acid, it could be base. What is it doing if it's in the presence of sulfide? So this time it's a little bit different. It's not just this dihydrogen phosphate ion in water, right? It's going to pass the H plus to water. This time it potentially might pass the football over to S minus 2. This guy here at first, well, it has an H as a negative charge. We're thinking amphiprotic, we're thinking it could be acid or base. What about the other guy? How about the S minus 2? Could this one here be acid? Well, to be an acid, you need to have an H. I need to be able to release off the H plus, donate the H plus. Well, I don't have the football. That sort of forces S minus 2 here to be a base. Remember, we can't have two bases on one side. So even though the H2PO4 minus could have been amphiprotic, the H2PO4 minus in this situation will prefer to be the acid. As the Bronsted Lowry acid, it currently holds the football, pass the football over. What ends up happening? Well, the H2PO4 minus is going to go down by an H, go down by a charge. I'm left with HPO4 minus 2, whereas the S minus 2 is going to pick up that proton here. It's going to go up by an H, go up by a charge. We're going to end up getting HS minus, right? So using this one proton transfer analogy, we can actually make really easy predictions for what the product's going to be. Now the football is currently being held by HS minus. That's the conjugate acid form. Currently, I've actually lost it. If I then receive the football back, I would then be the conjugate base. We have formed two conjugate pairs. Notice that conjugate pairs are on opposite sides of the equilibrium here, but we always have to have one acid and one base in the equations. Sometimes on the multiple choice questions, they're going to put a particular ordering of the reaction for you and just say, can you identify which ones are acid base, base, acid, acid base, and you basically mash it up to the way that they have it. We're going to come back later on to talk about which of these equations are one way. Most of these equations are going to be two ways. We now actually have set up a competition between, well, I have an acid that's willing to give up a football, and acid on the other side also willing to give up a football, depending on which one here is a stronger acid. All acids here give up footballs, but some break off a little bit easier than others. We can actually do our KEQ again later on to figure out whether products or reactants are favored. Okay. Now, I had mentioned here, especially when we did amphiprotic here, typically once we're neutral, we don't want to pick up any more protons. There's a special case when we start taking a look at organic compounds here. So let's do two special cases. One special case we've actually seen from before. That's basically if I have, let's say, chaku. Right? Chaku here is actually a carboxylic acid. All carboxylic acids have this COOH grouping. So I don't really care what's on the end of this one here. This one here may look like it's a base, but we had talked about earlier, well, the carbon and the oxygen bond is covalent. That bond doesn't break. In fact, because of resonance, this one here only breaks out to form the H+. So just look out for that here. If I have this COOH grouping that all carboxylic acids have, this one here, it's going to be a weak acid. So this one here is not going to break up 100%. It's going to be in equilibrium. We're going to end up getting just acetate. So to go down by an H, go down by a charge, and that proton will be typically picked up by water. The other organic case that we care about is the family of amines. And amine here, amines have the functionality of N something, NH2, NH, and whatnot. I'm going to do an example of methylamine here. So let me just draw this picture out for you here. We have a methyl group, CH3. I have an amine. You'll notice this one here is already, okay, it's a compound, it's neutral. I have no sense in picking up an H+. In this case here for methylamine, you see that although I'm overall neutral, I do actually have a lone pair. So this is the one exception that we have. If someone is willing to give me a football, I'm more than happy picking up that football. What ends up happening then is I'm going to take my neutral compound methylamine. It's going to pick up a football and then going to actually form CH3 NH3. And this one here is actually going to be positive charge. That's probably the one case that's weird where your compound will actually become a positive charge, and that was because the amine group here actually had a lone pair to actually attach to an H+. So if I do it pictorially here, basically most of it has not changed. The methyl, the N still had 2 H's, and now all it's done is it picked up one other H. That H here had an extra positive charge, so overall we become a positive compound there. All right. So do some your practice questions here. Make sure you're familiar with this Bronsted Lowry definition. We'll pick it up from there tomorrow. Thanks, guys.